So this chapter is on gravity and central forces, and we'll start with just talking about Newton's law of universal gravitation. I think he did this in around 1687, maybe. And it says that the force, the force on object I due to J, you can reverse those two and put a minus sign out here. But anyway, the force on I due to J is G times the mass of I times the mass of J over the distance between them. Rij is just the distance between them squared. And the direction vector is the direction that points from I to J. And so, you know, if this is m sub I and this is m sub J, and that's my R vector, points from I to J. So Rij is just the magnitude of the vector, like that. So it's GMM over R squared. That's its magnitude. Its direction is the direction of this vector. In other words, it's this vector divided by its magnitude, which just gives us a unit vector. And so sometimes you'll see it written as GMIMJ over Rij squared. And we can sometimes have a minus sign if you have the vector, if you choose to pick your vector pointing the other direction, pointing from J to I, and so it just depends on how you define it. But anyway, that's why we have it. And so it's the force on m sub I due to m sub J. Rij points from mi to mj. G, which wasn't figured out until Cavendish in 1791, is 6.67259 times 10 to negative 11th Newton meter squared per kilogram squared, plus or minus, 85 in the last two digits here. This was really the first physical constant of the universe discovered, and it's probably the least well known. It's very hard to make precise measurements of gravity because there's objects all around your lab, and so getting a really precise measurement is very challenging. Maybe we can do that in space somehow, but even then it's tricky because there are objects with gravity in space all over the place. And so measuring this constant is very tricky, unlike, say, the speed of light, which is known, I think, to 9 or 10 or 11 digits maybe by now, and things like that. Energy transitions in atoms are known very precisely. Okay, gravity is a central force, and that means that you can treat an object as though all of its mass is at a point at its center of mass, and then you can operate off that. Einstein had to prove that, and that's what he used calculus for. But there are certain forces that are central. The Coulomb force is a central force as well. It's also isotropic, and what that means is it's the same in all directions. So, if you draw a sphere around the center of mass of some object and you walk around on the sphere, the force is going to be the same everywhere on that sphere as long as it's centered on the center of mass. And so it's the same in all directions. That's what isotropic means. Newton was really the first person to get this. There was a lot of discussion at the time about whether Kepler's laws were known at the time. So let me just pause. So by the time Newton came along, Kepler's laws were already known. These were known around 1620, and Newton was born in 1642 and did all his stuff in the later. He invented his three laws of motion in 1666, and so that's sort of when his professional career began, and he lived till 1727. So Kepler's laws were already known. They were already really understood and accepted really by the time Newton came along. It may have taken a while into Newton's life, but anyone who is good at science sort of knew these were the laws that govern the motion of the planets. And so the laws were all planets orbit the sun in ellipses with the sun at one focus. And so, here's an ellipse. This is a crazy elliptical ellipse, but here's the idea. And so that's an ellipse. And so if this is where the sun is, let's use a little red star for the sun, say. Right, that's the focus where the sun is. Nothing's at the other focus, right? And then we can say, look, when a planet's out here, what Kepler's second law says is that when it's out here, it will sweep out an area equal areas in equal time, and so it's got to sweep out a much bigger area in here, a much bigger angle in here, in the same time to get an equal area. And so the planet takes the same amount of time to go from here to here as it does to go from here to here. And so we would call this conservation of angular momentum. When it's far away, it's moving slower. When it's in closer, it's moving faster. And we'll derive this in not too long. And finally, Kepler noticed by looking at Tycho Brahe's data that the square of the period, the orbital period, that is the time it takes for one lap, is proportional to the cube of the semi-major axis. Now the semi-major axis is really is this distance. If you take the center of the ellipse and draw a line, let's see, take that one. That's the semi-major axis. It's half of the major axis, right? For most things, we just call it the radius because our orbits are pretty circular. But that's what he said. He said the square of the period is directly proportional to the cube of the semi-major axis. And so when Newton was looking at apples and moons, he realized that the acceleration of the moon, and I'll talk about this in a few minutes, is very similar to what an apple is doing. He was the first person to notice that when the moon is orbiting the Earth, it's actually just falling, the same way an apple is falling. And he knew how to calculate the centripetal acceleration of an object. It was v squared over r. And so he knew that the speed was 2 pi r divided by the period. Again, I'm assuming a circular orbit for now. And so that means the acceleration of the moon, if I substitute this in for v, gives me this, 4 pi squared r squared over t squared. That's the v squared divided by r, that gives me that. And so if I remove the equal sign and go to proportional to, I can replace the period squared here with the r cubed here, and I can drop the constants because I'm just saying proportional to now. Is proportional to 1 over r squared. And so he knew from his laws F equals ma that the gravitational force was proportional to 1 over r squared. And that was an important sort of discovery for him. He also knew that by Newton's third law, Fij is equal to Fji, right? Or minus Fji if you want to put vectors in there. But the magnitude of these two forces is the same. And that's what led him to believe that the force due to two objects was proportional to mi, mj. Both masses had to be in the equation symmetrically so that the third law could be true over r squared. And so this sort of led him to the formulation that you saw on the previous page. There was a lot of discussion at the time. He was not the only person to recognize that a 1 over r squared force might be what gravity is. Robert Hooke and Christopher Wren and Edmund Halley were three scientists who met regularly at that time, and they were part of the Royal Society of London, which began right around the middle 1600s. And they had several discussions about whether or not a 1 over r squared force, a gravity force that was 1 over r squared, would produce elliptical orbits. And Newton had to work out the calculus for that. Edmund Halley was sort of the go-between between those guys and Newton, because Newton didn't get along with too many people very well. But Edmund Halley of Halley Comet fame got Newton to sort of fight his way through the mathematics of this, the calculus of showing that a 1 over r squared force gives the elliptical orbits that Kepler discovered, and that would explain the motion of the planets. And so Newton sort of explained all of this with his laws and the gravitational law of universal law of gravitation. So we're going to do a little discussion of the gravitational force on a particle of mass m. So here's my particle of mass m due to a spherical shell. So this is a shell of mass m, and we'll call it surface density rho. So it's a hollow shell, and what we're going to show, not on this screen but on the next one, is that we can treat it as though all the mass is centered here with regards to this particle. This particle just will see the whole shell as a single mass, with the mass of the whole shell centered at this point. And so I've defined a whole bunch of things here. Here's the center. It's got radius r. Here's my particle. It's at point P. The distance between them is little r. The radius of the sphere is big R. And I'm looking at just an annulus, a ring around the sphere. So it's just like you took a ribbon and went around the surface of the sphere at angle theta. And it should be a thin ribbon. It'll be infinitesimally thin at some point, but just for drawing purposes, I'm saying it's centered at angle theta, say, and it's got width delta theta as measured from here. And what we're going to end up doing is integrating from theta from 0 to whatever that is, pi, and we'll cover all of the elements of the surface. Right? This point Q is just one point on the surface of the sphere. This distance is r, that is s, this angle is phi. And so, first of all, we're going to focus on what this ring is doing to this point gravitationally. And so the first thing we're going to say is, well, look, the circumference of this ring, it's just a ring, is 2 pi times r sine theta. The radius of this ring here isn't r, it's r sine theta. It's this distance to its middle, say. Again, this would be infinitesimally thin. And so the circumference is 2 pi r sine theta. The area of the ring, I now have to include its width, is r delta theta. And so the area of the ring, the little delta area element for the whole ring, is 2 pi r sine theta. That's its length, times r delta theta, that's its width, right? It's infinitely thin, so we don't have to worry about its thickness, it's infinitely thin. And that means the mass of the ring is just that times the surface density, rho. It's rho delta A, so it's rho times 2 pi. I combine the r's, r squared sine theta delta theta, right? And so this ring is, all of this ring is pulling on this guy, and each element of the ring, like this one at point Q, is pulling it this way, but the element down here is pulling it this way, the element over here is pulling it, and the element that would be up here is pulling it this way, and so on. Everybody's an angle phi from the center axis, which connects the 2 points. And so they're all going to have perpendicular components, like if I were to draw this guy, there would be an equivalent force going this way, right, for this point here opposite Q. And so their perpendicular components would cancel, but their parallel components would add. And so if I want to know what the net force is on this, I can neglect all of the perpendicular points or just cancel them all, because at every point on opposite sides of the circle, the outward points will cancel, and the points on axis will add. And so I can say, look, the net force on this guy is just the integral of all of these delta f's, where I treat them as vectors, and that's just gm delta m over s squared, right? Where s is the distance between the point and the mass all the way around, except I have to multiply that by cosine phi to strip out the middle piece, right? And that gets the component along axis for each one of these little submasses. And so that's what the net force due to this ring is on the mass at this point P when I'm in angle theta and phi. And so it's gm and times delta m, which is 2 pi rho r squared sine theta cosine phi delta theta, or s squared. And that's going to be a little df along the axis. And then I'm just going to integrate this thing from theta equals 0 to theta equals pi. So this gives us, leads us to this integral. If we want to integrate over all the little delta f's for all the annuluses going all the way across that sphere, the force we get is just by integrating all of those. And that amounts to this integral. It's just, we carry out the integral over delta f, and that ends up being an integral over theta from 0, which is the forward direction. You can imagine your sphere sort of here, right, in this picture, right, where theta is this way, and then theta goes all the way back to that way. In the course of that process, of course, phi changes. And so this, as it's written, is not a trivial integral. Also, s changes, right? And so we have to figure out how to manage s and phi and theta in this integral to be able to evaluate this. And so we're going to use a little trigonometry here. First of all, if you remember the law of cosines, it's s c squared is equal to a squared plus b squared minus 2ab cosine c. S squared, the opposite side, is equal to the sum of the squares of the two other sides, r squared and big R squared, minus 2rr cosine theta. That's the law of cosines. We can differentiate both of those, and that gives us a relationship between ds and d theta. So if we differentiate the left-hand side, we get 2s ds. Since little r, which is the distance between the point and the center of mass, center of the sphere, is constant, as is big R, which is the radius of the sphere, those things don't change. And so when I differentiate these two, I get 2s ds on this side and 2 little r big R sine theta d theta when I differentiate minus cosine. And so the 2's cancel, and I get sine theta d theta is equal to s ds over rr. And so that takes care of sine theta d theta. It gets it in terms of s, and I have to do something with phi. And I'm going to use the laws of cosines again. I've already rearranged it a little bit, but it's exactly the law of cosines, except about this angle instead of about this angle. And so what we get is cosine phi equals s squared plus r squared minus big R squared over 2rs. And notice this gets phi, cosine phi, in terms of s also. And so that if I rewrite this equation down here with all of the s's substitute, I substitute in this quantity for sine theta d theta. And so this is sine theta d theta, and this term here is cosine phi from the law of cosines. Then all I need from here is 1 over s squared, and that takes care of that. And now I've got an integral that instead of going from theta equals 0 to pi, it goes from s is equal to little r minus big R to little r plus big R when it's on the opposite side of the circle. And so I have an integral that's going from r minus big R to r plus big R of ds, where I've combined terms here. And so this is a not very difficult polynomial expression. Remember, little r and big R are both constants for the whole calculation. Big R is just the radius of the shell, and little r is the line connecting the point to the center of the circle. And so those are constants. And so this is an easy integral to do, and we'll just do it on the next sheet. So now we're just solving a nasty integral, and this is just a little more detail than your book gives you. Force of gravity can be written this way. I've just factored out the 2r squared. Again, the limits of the integral are so that it works for ds. I have only one integration variable. Little r and big R are constants. If I want, I can take into account the mass of the shell. The mass of the shell is 4 pi r big R squared times the density. Remember, that's just a surface density, and so I can group these guys to make the mass. If I put another factor of 2 in the denominator, then that gets this. And now I'm integrating this fairly simple function. And remember, the integral of 1 over s squared ds is minus 1 over s. And so when I integrate this thing, I get this term unchanged. This is just the coefficient out front. And when I've integrated through, the 1 becomes the s, and this term becomes this guy. And then I just kind of have to plug in and evaluate those things. This is that evaluated here, and this piece is that evaluated here. And when I do all that, I get all my little r's to cancel. That one and that one and that one and that one all cancel. And these guys become 2 times big R, and I get 2 more big R's, so I get 4 big R's, which cancels with that, which gives me GMM over R squared. And again, it just, the whole point of this was that integrating over that whole surface that we started with, that whole spherical shell, is equivalent to having a force that has the mass of the whole shell at the center of mass of the system. And so if you treat a spherical object as an infinite succession of shells going outward, then it's clear that the mass of the whole spherical shell, the solid shell, rather than just, the whole solid sphere rather than a shell, will also have its center at the center, because each concentric shell of that solid sphere will have this. And so if this is a solid sphere, the equation will look exactly the same, where the big M is the mass of the solid sphere. This is why Newton invented calculus, to solve this problem. Well, one of the reasons.